Hello everybody. Let us just continue with our second chapter in metamorphic petrology. At first we are starting with some very general things. So metamorphic rocks are rocks which underwent a transformation that we are calling metamorphism. And these metamorphic rocks has been before either igneous rocks, sedimentary rocks, or other metamorphic rocks. So, and this transformation from one rock type in another rock type is caused by pressure and temperature changing in the Earth's mantle and in the Earth's crust. So these are the two most important controlling factors. So, but the next thing is the bulk composition of our protolite. So, for example, if we have a silica-rich protolite, then we can expect after metamorphism also a silica-rich metamorphic rock. If our protolite was rich in calcium carbonates, then we can also expect afterwards a metamorphic rock which is rich in calcium and which has CO2 as a main bearing fluid. So here on our first slide I have three pictures from or sketch maps from thin sections. Sketch map A shows us the mineral assemblage of wollastonite, quartz and calcite. Section B as well, wollastonite, calcite and quartz. And the same for section B. But the volumetric abundance of all these minerals inside is totally different. So for example, in section B, we have more wollastonite inside compared to section A and section C, whereas in section A we have much more quartz inside compared to section B and C. So, but all these three rocks in these three different section has been formed under the same pressure and temperature conditions, but the volumetric abundance of the rock forming minerals is different, and that is due to the fact of variations in the bulk chemistry. So in metamorphic petrology we are using always projections. So these projections helping us to simplify very complex relationships. So, and for every rock type we are using certain chemographies. For example, for metapelitic rocks are have been before, or the protolite from metapelitic rocks are aluminium-rich sediments. So therefore we are using an AFM projection. A stands for aluminium, F stands for iron, M stands for magnesium. And with these three components we can already form a number of different minerals. So here on the left hand I have written quartz plus muscovite plus water is in excess. So that means that was a silica saturated sediment. So if we are talking about sediments, then we can assume or suggest that H2O is also in excess, because water is always in excess in such aluminium rich sediments, and that is because of the deposition of the sediments. So then we have the muscovite in excess. Muscovite is an mica, it is a white mica, and that has potassium. So that is potassium, Al2, Al, Si3, O10, OH2. That means we have now 4 components, no, we have even 5 components in the system. We have aluminium oxide in the system, we have iron oxide in the system, we have magnesium oxide in the system, as well silica oxide, and we have potassium oxide in the system because we have put quartz and muscovite in excess, as well as water. So that allows us also to form or to project hydrous mineral in our AFM projection. Here at the top, where we have aluminium, we have following minerals plotting there. We have the kyanite, which is Al2SO5, the silicimide and the andalusite. These 3 minerals are polymorph minerals. Then we have the pyrolusite and the kaolinite, which are minerals formed at very low pressure and temperature conditions. Then we have here next to the staurolite, and staurolite is a very famous mineral, especially here in Namibia, because you can find a lot of staurolite bearing schists. Then we have here the chloritoid, and on the other side we have the cordierite and the spinel. Then we have the garnets here on the iron-rich side. We have the almandine, which is the iron bearing garnet, and on the other side we have the pyrope, and the pyrope is the magnesium bearing garnet. Below we have the chlorides. Here is the chloride. Then there below we find the pyroxenes. Here on that side we have the enstatite, which is the magnesium-rich pyroxene. And to the other side, to the iron side, we are getting a more iron-rich orthopyroxene, which is then called the ferrosilite. So here below the iron and magnesium, we are plotting the biotides. Why? The reason why the biotide is plotting on the negative side, I will explain to you later. So, and here the biotides making a complete FM exchange. Here on this side, on the left side, we have the iron-rich biotide, which is called the anide. And here on that side, we have the phlogopite-rich biotide, which is called the phlogopite-rich biotide, which is the phlogopite. So here the biotides making a complete iron-magnesium exchange from here to here. The orthopyroxenes are making not a completely iron-magnesium exchange because the iron end member ferrosilite is not stable in nature. So the chloride makes also not a complete iron-magnesium exchange, but the garnets, they are making a complete iron-magnesium exchange, seen here in that line. The cordierite is also only making a certain an iron-magnesium exchange to a certain degree up to here, as well as the chloritoid and the staurolite as well. So now when we are looking at the phase fields or the chemical composition fields for the biotides and the orthopyroxenes and as well as the chlorides, then we can see that here the barrow is much more thick, yeah, compared to the iron-magnesium exchange of the garnet. So why is it here more thick? Shown in this light shaded area, that is because of the Cermak substitution. So in this Cermak substitution, you should already know that from the third year when we are doing the introduction or the mineralogy. The Cermak exchange, that is the exchange between silica plus magnesium will exchange with 2 aluminium. So that is the typical Charmak exchange. Here we have here written AM. So A for the 2 aluminiums and M for magnesium plus silica. Aluminium has 3 electrons in the outermost rim, so 2 aluminiums are 6 aluminiums, whereas silica has 4 electrons in the outermost rim, and magnesium has 2, is then also 6, so we can do this exchange. If we are doing this exchange on that side, then we are talking about an iron Charmak. That means 2 aluminium going for iron plus magnesium. So going to our next projection, also an FAFM projection, then we can subdivide our triangles in different phase fields. So we have a three-phase field like this one here, consisting of garnet, sillimanite plus biotite, or this one here consists of cordierite plus sillimanite plus biotite, or this one here consists of biotite, garnet and K-feldspar. Then we have a one-phase field, that is this one of biotite. And we have two phase fields like here this one between biotite and cordierite. So depending on the bulk rock chemistry, which I have mentioned to you at the beginning, we can have at a certain given pressure and temperature either this stability field of these 3 minerals, or that one, or that one. So if we have a mineral assemblage consisting of garnet, sillimanite and biotite, that means we have sillimanite in the system, then we have more aluminium. Whereas if we have biotite, garnet and K-feldspar in the system like here, that means we have in the bulk rock chemistry more potassium. So, and if we are looking at this one, with cordierite, sillimanite and biotite, then we have more magnesium inside. So, but we can have in one rock sample at a certain pressure and temperature, we can have only one of this. So, and along this line here, the garnet makes his iron-magnesium exchange, and along this line here, the biotite makes his iron-magnesium exchange. So, and then it depends also on the bulk rock chemistry. For example, if we have the mineral assemblage between garnet, sillimanite and biotite, then our biotite is more rich in iron. Whereas if we have the mineral assemblage between sillimanite, cordierite and biotite, then the biotite is more rich in magnesium. So now we are dealing with another projection. We are dealing with the ACF projection. The ACF projection is used for metamorphic rocks. A metamorphic rock has as a magmatic precursor, or as the precursor for this kind of rocks, a basalt or a gabbro. Yeah? So because when we are looking at the basalt, we have a lot of plagioclase inside, and that means we have a lot of calcium in the system. We have also a lot of aluminium in the system, and we have a lot of iron in the system. So then we are putting quartz, CO2 and H2O in excess, because in these basalts we have also CO2 bearing minerals like calcite, for example. So, and therefore we can span our triangle with a lot of different minerals. Here at the top we have again A, and that is for the alumosilicates. I wrote here the kyanite. Then we have here C, and C that is for the calcite and for the element calcium. So, and then we have here iron, and this iron here stands, here we plot in the mineral talc. So then within this triangle we can have a different mineral assemblages. Here we have the garnet doing here the iron calcium exchange. So here we have the amphiboles, and then we are doing the Charmak exchange within the amphiboles. Here we have also some dolomite plotting. Then here we are doing calcium iron exchange. Here we have the mineral suicide, and here in this field we have then the phase field consists of kyanite, garnet, plagioclase, and here below we have then plagioclase, amphibole and garnet, whereas here we have garnet, amphibole and chloride, or here we have amphibole, chloride and talc, or here we have the calcium, the amphibole and the suicide. So whereas, and that I have also to mention, here we have talc, and talc is actually Mg3Si4O10OH2. The iron goes here together with the magnesium. So here we have the next ACF projection with some more minerals inside. For example, here we have the diopside inside additionally, yeah, that is the clinopyroxene. Then we have pumpelite here inside. Pumpelite is a zeolite, and it is very hydrous and is stable at very low temperature conditions. Then we have here again the staurolite, and here we have cordierite, chloritoid, and the calcium, iron, magnesium garnets. Here again the chloride, and here at this corner the OPX, the autoamphibole and the talc. Whereas we have here the epidote, zoisite, phrenite, grossular. Here we have the margarite, which is a white calcium bearing mica, and here we have also the plagioclase. So that is, if we are adding muscovite to the system, then we have also potassium in excess. So, how does such reactions working? So you have maybe now heard about the Gibbs free energy, and if the Gibbs free energy is zero, then no reaction will take place. Then we are talking about equilibrium. So, and then we have here the temperature at equilibrium. So that means at this point we can have the mineral assemblage albite plus quartz plus jadeite, yeah? When the Gibbs free energy is zero, then we have the equilibrium of this reaction. When the Gibbs free energy is not zero, then the reaction is not in equilibrium, and then the reaction will take place. So then the albite, when we are going here from A to B, then the albite will react away, and we are forming then jadeite plus quartz. Jadeite is a pyroxene with the mineral chemical formula NaAlSi2O6, whereas albite is NaAlSi3O8. So, and the reason why we have on both sides of the equation quartz is because the whole system is saturated with quartz. However, the reaction itself is jadeite plus quartz is albite. So, and the reaction goes always to that side where we have the lower Gibbs free energy. So, when the lower Gibbs free energy, that is always a minus value. So, in the more negative value of the Gibbs free energy to that side, the reaction will go. So if we are starting at B and we have on this side a lower Gibbs free energy of the reaction, then the reaction will go from that side to that side. So, and this is caused by pressure and temperature changes. For example, here we have a nice picture from an outcrop. That is actually a huge outcrop in Switzerland. We have here the scale at the bottom at 100 meters. And there we have a huge lens of Harzburgite inside. In a granite. And such a granite, you know this by now, consists of quartz, K-feldspar, plagioclase, and plus minus biotite. The Harzburgite you know by now as well, that is an ultramafic rock, which normally occurs in the Earth's mantle, consisting of the minerals forsterite and enstatite. Forsterite is an olivine with the mineral chemical formula Mg2SiO4, whereas enstatite is a magnesium endmember of the orthopyroxene with the mineral chemical formula Mg2Si2O6. But you can also call it MgSiO3. Both answers are correct. So, and around this Harzburgite lens we are forming a zone of talc and a zone of biotite. So, in this zone of talc and zone of biotite is formed because the Harzburgite lens was not in equilibrium with the granite. So when the Harzburgite lens is supposed to be older than the granite, and the granitic melt has picked up this Harzburgite. So that means the granitic melt was probably hot, can be hot, up to 900 degrees Celsius, has picked up the Harzburgite lens. We are not in equilibrium, and if something is not in equilibrium, then a mineral reaction will take place. So then close to the biotite, so close to the granite, we are forming a zone of biotite, and close to the Harzburgite, we are forming a zone of talc. Why is this? This is because the Harzburgite is rich in magnesium. Then we can make, or we can form close to the Harzburgite a zone of talc. Because the talc is magnesium rich, it's Mg3Si4O10OH2. So, but then the silica, the granite is silica saturated. The silica will go from the granite towards to the Harzburgite as well as the potassium. And this potassium and silica we need to form the biotite. Yeah, you know the biotite has in the interlayer potassium within the different TOT blocks, whereas the talc is empty there. So, and these are diffusion controlled reactions. So, and this reaction will take place as long as equilibrium conditions are reached. So, here we have now a sketch map or a cross section from core to the mantle to the surface. And on the right hand, we have a temperature at the core mantle boundary diagram. At the temperature of the core mantle boundary, we have very high temperatures, and these temperatures becoming lower towards to the surface. So when this heat is transported to the surface along a thermal gradient, so that means if we are going here from the surface along Z, then we are heating a certain piece of rock. If we are sending a certain piece of rock from here to here, we are heating this piece of rock up. So that means exotherm reaction will take place, and the whole process is then prograde metamorphism. If we are bringing a volume element of rock from the core mantle boundary towards to the surface, then we are talking about retrograde metamorphism, and endotherm reactions will take place to our rock sample. So in nature it looks then more like this. We have region with a high heat flow, then we have, which we can see here, yeah, that is just here at the continental crust. Then we have regions with a very high heat flow, that is at the middle ocean ridges, and at the middle ocean ridges we have a young oceanic crust. So and while or due or when the oceanic crust will become moved here to the right and from here to the left, then it will cool down. So herefore we have then an old oceanic crust, and this old oceanic crust will grow, it will become more and more thick till it becomes subducted, and there we have then a very low heat flow. So and here in the lower and the upper mantle we have then the convecting mantle, and here in the middle, here beneath the middle ocean ridge, we have then ascending plumes, and here we have descending plumes.